as per algorithm. Right, but there is a drawback in this circuit. What is the drawback? From my design point of view, it is the best possible way. Okay, but when it comes to foundry, foundry will say that चलेगा नहीं, ज़्यादा पैसा लगेगा. Why? Because it is no more regular. Some places half adder, some places full adder. I need to change my technology every time. Regularity is not there. And in VLSI industry, we say that mass production, regular structure, regular layout will charge, will be less, right? Easy to fabricate. So from fabrication point of view, this may not be a good strategy, right? So from fabrication point of view, what we should do? We should look for all the half adders, translated into full adders. Okay. Maybe some resources will remain idle. But then what is the advantage? You can use them as a fail-safe operation, right? So if some of the half adder on the chip is not working, probably you can multiplex and pass the input and get the work done instead of discarding the IC. Okay, so there are architecture which will say that their goal will not be to optimize the hardware. Rather, adding extra hardware such that even if there is a fabrication issue, the chip you should not throw. Rather, you should be able to reuse it. Okay. So, so now replacing every half adder with full adder. And wherever there is a half adder, I don't need other two bits. Okay, so whichever bit is not required, just for this production of this bit, we don't need this. So both inputs are 0. Okay. So everywhere half adder will get replaced with full adder. Some resources are restricted. Okay. Now this is the half adder, full adder, and then another, because here there will be carriage generation. We need to accommodate it. Okay. Now where the critical path is? Again from LSB to MSB. Okay. So now I'll add a concept of pipeline architecture. So can we pipeline this? Yes. So where do I insert pipeline so that it becomes optimal usage of pipeline? See, one solution which is coming up is that what is suggested is here, right? At this place, at this place. Is it? Right. Then other is to write here, right? Where? Okay. So what will happen now with this? Do I need to add a flip flop here? Projector here? Yes or no? Huh? Tell me confidently, yes or no? Huh? We don't add, if we don't add, then this result will be 2 clocks delayed and this will be 1 clock delayed. So there is a result mismatch. Okay. So if this is delayed by 2 clocks, this should also be delayed by 2 clocks. So that the result will be output at the same time instance. Otherwise, there is a bit mismatch. So even though you are busy having this as a fast path, you have to insert flip flop. There is no choice. Alright. So what will happen? Another. Correct? Then one more. right? Then what will happen? So how many flip-flops do you think register? All the green lines, whatever we have drawn, minimum those many are required. Alright? That is it a correct solution?
There also there will be some mismatch because last two letters taking some generate 245 pieces.
Even though you start working here fast, you need to hold on this for 4 adders to complete their operation. Right? So is the solution proposed optimal? No. Unnecessary inserting pipeline in hardware doesn't mean that your performance is going to improve. Because here you are taking delay of one full adder, whereas here there is a delay of 4 full adders. So what the gain you are going to do? Get. You have to wait for such 4 full adder delay. You have just increased power consumption and area and latency of your design. Because the now results will be available after these many clock periods. On top of that, this clock period is dependent on this path. Right? So there is no gain. So what is a good solution? This is what is the scenario. By the time I reach from 1, 2, 3, 4, and we have 4 here. Right? So can I have this as one stage and this as another stage? So that here there are 4 full adder delay and to this side also it is a 4 full adder delay. And hence my critical path is getting balanced. Isn't it? So what we need to do? Insert flip-flops at appropriate place so that it becomes pipeline architecture with low latency and low area. It's not that blindfolded you will insert pipes wherever you would like. Okay. So optimal place for insertion of pipeline is also important. Here, take a point why it is inserted here, because it is 4 half adder delay, and here also it will take this much delay, 4 half adder delay, and probably equal. So throughput is delay latency is 2 clock cycles. Even though you are not looking for this, you have to insert so that synchronization between the result bits will take place. Clear? Is that clear? So when papers you write, you be careful. People look for this. पाइपलाइन बता रहा है ठीक है क्रिटिकल पाथ का सारे स्टेज में उतना है क्या मॉडरेट अप्रोक्सीमेटली उतना है क्या अगर है तो ठीक है नहीं तो पहला रिव्यू कमेंट वहां जाएगा ओके so these are the important things okay pipeline stage will now improve why because now your critical path earlier it was 1 over 8 now it is 1 by 4 full adder delay right penalty area increase because of flip-flops. Okay, so that is what we said all the time, right? एक ऑप्टिमाइज करने जाते हैं दूसरा बढ़ता है पता नहीं कैसे डिजाइन करना पड़ेगा so that everybody will get compressed. Okay. So I'll keep this part as a typical execution. It will take long. Okay. we'll go to this simple and similar architecture. That was okay for unsigned bits. What is signed bits? Multiplier for signed number system. So signed number system again revised. MSB is meant for sign. Other bits are meant for magnitude. Okay. So sign magnitude representation. Right now I am using. Okay. So what will happen? Now I don't have choice other than sign extension. So the gray box is nothing but sign extension. Whatever is the sign of this bit is extended. Sign of this bit is extended. हो सकता है negative हो तो ये 1 हो, positive हो तो 0, right? So we have to extend that sign bit. Okay. What is important when we are looking at this? If both numbers are negative, what will happen? Both number will have this bit is equal to 1, right? So if both numbers are having this bit is equal to 1, what will happen? The number magnitude will become negative. Okay. And for the rest of the time, it will be added, and this time it will be subtracted. So earlier architecture and this architecture, what is the difference? Number one, sign extension is required. Number two, last partial product has to be subtracted. Okay, last partial product has to be subtracted. एक नंबर 0 है, एक नंबर पॉजिटिव है, 0 है, नेगेटिव है, तो क्या होगा? Product is 0, so this term will be 0, right? And then only addition will come. Okay. If both are 1, this term will be there, and then you will subtract. Okay. Does it really work? We'll see. Okay, don't worry about that. I'll take you through an example. Okay. Representation of 4 and minus 4 using sign magnitude. Okay, no more 2's complement. Sign magnitude. Okay. Representation of 3 and minus 3. यहाँ पे क्या है? नहीं, 2's complement. Sign magnitude and 2's complement. Okay, 2's complement. Okay. So minus 3. Okay, so what is the number? Minus 4 multiplied by minus 3. Okay, so minus 4 minus 3, 2's complement. Okay. Okay. Now we know the algorithm. We have to multiply this. This is one is the same bit pattern, extension of the sign for the upper bits. Okay. M bit multiplied by n bit. Answer is m plus n bit. So we have to extend for those many bits. This is 0. Makes no sense. Everything is 0. Sign extension is also 0. Adding these two, what is the result? All bits 1 except last 2. Correct? So now third time what I need to do? This has to be multiplied and added here. Right? So I'll pull this here. Okay. All bits except last 2 are 1. And now this starting from here has to be added. Okay. What is the answer? 20210. Okay. So now 20210, and now I am going to do subtraction. Subtraction of what? This multiplied by this and sign exchange. To be written here, right? Now subtraction. After the subtraction, what is the answer? Minus 3 multiplied by minus 4. What is the answer? Is it not correct? There is no magic. Okay. Now, say one number positive, other number negative. And I need to check because both negative it work. Both positive it will work. One negative, one positive. Okay. Now you can understand what is happening. Okay. Last result. Subtraction with 0. Answer remains the same. Right? What is the answer? This complement of the right? Works? Okay. How to do that? We know now the idea. Okay, we are just mapping it on the circuit. First partial product, sign extension with. Okay. Second partial product, sign extension of the bit to be added. These are can color are nothing but sign extension position. Third partial product, addition, sign extension. Okay. Final partial product, I want to do subtract. Subtract with what? 2's complement addition. So 2's complement is nothing but 1's complement plus 1. So 1's complement instead of and we have done and this full adder we have given carry is equal to 1. 1's complement plus 1. Signed addition. Signed multiplication. Right. So if somebody asks you to do such kind of things, don't get shattered. To try with bit patterns. Okay, what will happen? And combine all these bit patterns, you can find out what should be the underneath architecture. Okay, let it be not optimized. Who cares? Getting solution is first goal. Okay, optimization takes place later on. Right? Now, somebody come up with this, what are doing? There is redundancy, is not optimized. I have an elegant solution for this. Okay, and those were Bahubali. Okay, 1973, I think. They proposed the idea. Here, carry is discarded. MSG. Why? Any carry generated is discarded. Number 16 says that if it is a 1's complement subtraction, carry generated needs to be added. 2's complement carries needs to be discarded. Fundamental thumb rule. Okay, brush up basics. Okay. So now, in next, we have done this so far. Okay. Then there is a problem. Why do I need to add so many redundant things? Can't I simplify it? Okay, so that is what I am saying. Bahubali has come up with another idea. Somebody has proposed that. So every time some researcher will say, "Arey, uska to kharab hai, mera bahut acha hai." Okay. You have to accept the fact. It is happening since last few centuries. Why should we wait? तो किसी ने कुछ प्रपोज किया आज उसको ओवरराइड कर दे इन्होंने टू कॉम्प्लीमेंट up to this idea is same. Okay, this is what is the thing we are doing in the last row. 2's complement addition. 1's complement plus 1. Okay. Now what is suggested is that I will not touch anything. Rather, I will add 1 and subtract 1 and every partial product. So plus 1 minus 1 makes no sense. It's 0 change, right? But it is going to help us in optimization. So that is what is this idea. So what it is? साइन एक्सटेंशन जहां पर है वहां पे +1 -1 करके रखा, ठीक है। ये तो टू कॉम्प्लीमेंट का वन है, ठीक है। देन व्हाट विल हैपन at this place? If both are answer is 0, it may happen because one of them is 0 or both may be 1, right? I'm looking at that condition. If both are 1, what we need to do? Will result into addition 0. Okay. Otherwise, the bit will get toggled. Right? Clear? A3B0. If it is 1, what will happen? A3B0 is equal to 1. So what are we doing here? 1, 1, 1, 1. And all 1 plus 1. What is the answer? 0. Carry is discarded. The answer will result into 0. Fine. If this bit is equal to 0, what is the extension here? All zeros. All zeros plus 1. What is the answer? 1. I am not considering about this -1, only this much. So what is left out part? -1, not taken care of. Right? So this bit will be true. It is nothing but its complement. Okay, either if it is 1, it will be 0. If it is 0, it will be 1. To complement that bit. Okay. So the same I will repeat to all partial products. Okay, and where we are doing it? At the position where the MSB is aligned. Okay, so for this, so we have taken care of this complementing and subtracting 1, which was left over. The same idea will be applicable at all places. Okay. And here complement of complement, because it was 2's complementary number. So it is true bit -1. Okay. Now, if we look at the ones which are spanning along the columns, they are starting from here 1, -1, -1, -1, -1 in all the columns. Right. So what is that number? 1, 1, 1, 1. Right. So 2's complement of that. All 1, 1, 1, 1. 4 ones, which we are subtracting. If we take 2's complement of that, is nothing but, correct? So if I subtract that here, what will be the new number? This I need to add, right? Is that clear? So what is happening? You need to just complement the MSB position, and then you have to add a constant which will be like this. So for the first column it will be 0, for the subsequent column it will be 1 and then 0. And this becomes a constant number to be added. Okay. And now, if you look at the structure, this is what is the resultant 2's complement here. MSB position complemented, others are AND gate. This one is NAND gate. Okay, so realizing this term. Okay, this was 2's complement adder. Okay, so complement of complement, this should be true. So here it will be AND gate, other places it will be NAND gate. Right, and then what we need to add? In this column we need to add 1. Okay, so that is what is done. Okay, 1. Where is that? 1. Here is the final one, and typical one is feed. Okay, B3 half adder. Okay, here this position. It was not shown in the previous slide, right? So half adder is implemented for adding instead of that full adder, it is half adder now. Okay. Earlier here it was full adder, right? Plus one carry to first tooth complement. It is subtract. And then this becomes a tooth complement multiplier, which is proposed by Bauli, so known as Bauli adder, a multiplier, which has got similar structure like previous one. No redundant architecture is required. Okay. Hardware is required, but it can work for positive as well as negative. Okay. So this paper Baul is available, published in 1973. So then there are different multipliers, Wallace multiplier, tree multiplier, etc., etc. Okay. So what I wanted to convey is that try with your algorithm with certain numbers, possible values in your algorithm. See what is that happening. Okay. And it is not possible manually all the time to see all the possible combinations. So what is suggested way, if you remember, the first step I said that do high level language simulation. Okay, whatever algorithm, we try to implement it using Python, MATLAB, or C, C++, any language. Then you will come to know that अच्छा इस कंडीशन में रिजल्ट ये आना चाहिए था, मेरे हार्डवेयर में कुछ और आ रहा है. So you can cross check. You can by that you can understand what are the operations required, which part is sequential, which part is combinational, what is the boundary condition which I need to take care of. Okay, by some, but if you put here numbers all one, then it is a boundary condition. Okay, intermediate will work if it is working for boundary. Okay, so what are the things which you need to? Otherwise, sometimes you will come up with hardware which may not be optimal. Here, so don't start your work blindly. Have some. If you are having algorithm, try to implement it in higher level language. Understand which part you can partition into what side. Okay, and then you will come to know that अरे ये तो बहुत बड़ा ऐसे नहीं होगा. Then you start partitioning your architecture and do modular design and test only that particular module. Either it works under all circumstances, then you should not touch it. Okay, it is done. Then you will freeze all your other module, start working on that. And then finally you try to stitch them. By that time your thought process will also be clear. कि ये करने से ये होना चाहिए, ये करने से ये होना चाहिए, ये इस पे डिपेंडेंट है. Okay, clear. So these are some standard architectures which are available. Okay. And the if you look at my multipliers, these many multipliers I have read. Okay. So maybe there is a paper. I need to check somewhere. All these papers are available to you if you are having IEEE subscription. They will not. This is a suggestion. So these all papers have come in the side multiplier or something. overflow detection. So don't restrict yourself to read from any particular paper or any particular book. High speed binary arithmetic. I don't know. Somewhere I'm not. But what is you can see that the date of publication. Okay, if you look at this, when is it published? High speed binary computer architecture. Okay, January somewhere long back, adults. Okay. 61. January 61. People tried something high speed arithmetic in binary form. Okay. Computers were not available. Okay. Okay. So you will be able to do that. Okay. Literature is available. Can think of. Okay. So now what I will do is I will go to other topic. Okay. What we usually look into the uh, multiplier. One more possibility. Both multiplier is usually taught, so I am not covering that. Both multiplier is one can easily understand. Barrel shifter is very interesting. Barrel shifter, how to do, how to design. You don't need too many things to remember. Okay. Let us do some structure here. शिक्षा 5 बिट करता है. I like smart boards for this purpose. It reduces my burden. Okay. Now, seems to be complicated, which is not the case. Okay. Because you are saying these are the regular structure, copy paste. Okay. That is what typical technology will also ask for, copy paste. Okay. Yes, maybe yes, two, maybe yes, one, yes, zero. Okay. And simply connect it in this way. इसका कलर बीच में कैसे क्यों आ रहा है? You will understand the only one and you can draw it. Let us put a condition that one select can be high at a time. Okay, let us put that condition. So under that condition, what will happen if all bits are zero? This is the output. If all select are zero, what is the output? Output is equal to input. No doubt. Okay. Now what is I am interested in is I want to rotate this number, multiply this number by 2. Okay. So what is the rocket science in that? What I can do? I can pick this line, okay, and I can pass it here. Shifted by 1 is nothing but multiplied by 2. Okay, I'll pick this and connect it here. And I'll say that UB equal to 0, pull down keyword. And now if I say that in truth table, if this is the case, then number D is equal to D out is equal to 2 times D. Agree? You got it. Right. Next time what I'll say that no. I will use this is equal to 0. Okay. And I will make this side is equal to 1, this side is equal to 0, and number must be D out is equal to D times 4. What do we need to do? Lower 2 must will compare to 0. Right? So what is logic? To this 0, to this 0, and then skip and pass the output, right? So that is what is the barrel shift trace. Okay. So this will go here, and this will go here, this will reach from here to here, and so on. Okay, so this will be, so you will have some boundary condition. What is the minimum number you can, maximum number you can multiply? Now, if you want to multiply the number by 8 times, next time, suppose I will say that no, I will keep this bit pattern is equal to this 0 and this 1, and number should be shifted by 3 times so that I will get D out is equal to 8 times D. All right. Isn't it possible? Right. So that is what is a barrel shifter is. Barrel shifter is nothing but huge chain of multiplexers. DSP chips, TI chips use this concept of multiplication. Okay. Now we can add complications. Okay. Every single simple step I will add complication. Okay. So what is that? If I can do this as a rotate 2 to the power n shifting, left is multiply by 2 to the power n. If I change the direction, divide by n 2 to the power n. Okay. So you can have one more stage in between inserted, and you can decide either to shift by multiply by 2 or divide by 2, multiply by 4 or divide by 4. Okay. is other option. Okay. Third option. I'm interested in barrel shifting, circular rotation. This which is going out can be tied here, and this can be made flexible through another ones. Okay, then it becomes circular shift, right? How we circular shift? You decide and do it. Okay, circular shift left, circular shift right. Got it? And that is what all DSPs are. Okay, barrel shifting used with rotation shift. Okay, rotate with zero, rotate with the same number. Okay, so all such multiplexer based design you can do, and it becomes a combinational part. And how you add that complexity, depending on that, your critical path will change. Okay, so I am leaving it up to you to add that complexity and analyze. Okay, and then you can say that okay, if you are using this mnemonic, this operation. You are using this mnemonic, this operation. Okay, and that is how instruction set can be derived. Okay, here barrel shifter. You don't need to study a lot of books for that. Okay. In the next level, you will just do this 3-0. Okay. And then LSB will go skipping 2. So that is another way of multiplying the number. Okay. Now coming from this, let us do one more implementation. Okay. Suppose I have been asked to do A is equal to 1.25 times some value, maybe signal B, plus 8 times B. This may be line in your algorithm. Now, how to realize this? What should be the hardware? 1.25. Floating point. Fixed point. I don't know. You have to tell. That is your choice, right? Shifting will help. Instead of writing multiplier unnecessarily, what you can do? A number A shift right by 2 times. Okay. And then number A shift left by 3 times. Number B, right? Not A. In the algorithm, it is B. B. Okay. And then this is RTL of your design, right? And then there will be, depending on the, because now we are doing shifting, there will be clock, reset, okay, load, because you need to load this value. While you are loading this value, it should get copied in this too also, right? So there will be some load signal, there will be reset signal, then there will be clock signal, So what is important? Another thing. See, why you need to have rough idea. How many cloths will be required here? Two. Two cloths. And while we are performing this rotation, I am completing this addition. Okay. And then in that result, I am using. So this can be shared. Right? So resource sharing. Okay. So plan your data flow appropriately. To, truly speaking, we feel that okay, I need a floating point multiplier, एक fixed point multiplier, दो adder, एक adder, ऐसे नहीं, थोड़ा सा सोचना पड़ेगा क्या कर सकते हैं, ठीक है? That is why I said that every tool vendor will claim our design, our tool can implement multiplication and division. और धीरे से asterisk में बोलेगा 2 to the power ये ना, अरे वो तो सबको आता है. For the shifter is there. Okay. So now if you want this design to be purely combinational, what is the solution? Purely combination. I don't have this cloth, reset, anything. Okay, I don't have. I want this to be purely combination. Just now अभी देखा हमने बैरल शिफ्टिंग, ठीक है, लेकिन ये तुम्हारा एक फिक्स्ड है, बैरल शिफ्टिंग की भी जरूरत नहीं है. तुम्हारा इक्वेशन जो है वो फिक्स्ड है, राइट? सो व्हाट इज बी? सम नंबर. Okay, maybe 40b. Okay, so what I'll do? Hard multiplier. Okay, by concatenating these three bits. Okay, and then accordingly by shifting that, I am going to get 0.25. So I'll lose these. Okay, and I know this and the original number together will tell me 1.25. So hard multiplier. Because my goal is not to do multiplied by 2, multiplied by 4, and then come to multiplied by 8. Why I am increasing my critical path and hardware? Okay. Try to understand what you intend to do, and then you know how to write this. Just by concatenation, you can finish the task.
Is implemented a multiplier.
Yes. It will not use in multiplier hardware. Hardware direct crowds you will see.
Just add 3 zeros. Add.
No multiplier will be used. Direct wire. So what will happen? Your critical path will reduce. Hardware is reduced. Power consumption is reduced. Right? It's a win-win situation. Just for sake of implementation, like in C, C++, Python, again, the thumb rule says that, right? Having knowledge in higher level language doesn't mean that you are a good HDL coder. Okay. मैं क्या करना चाहता हूँ, करूंगा तो कैसे करूंगा, सिंपल वे क्या है? ओके, क्लियर? Now let us look at some typical, simple, but I know we have to do. We have done this, right? Choose complement of this. We have seen in multiplier we want this. What is that we are doing? One's complement plus one. Okay. So what is the two complement algorithm hardware realization? बिना इसके भी चला सकता है जो कोई बहुत सारे पॉइंट बोलो हाँ पेट्रोल कूलर
Four feet, then LSB is the operator and other student.
every bit which will be happen every bit because what we are doing we are adding this okay carry which is second bit there is no third bit okay carry which is second bit okay what is implement it in this way now what tool will implement who has no idea so we will simply go ahead with full adder but is it optimized गार्बेज इन गार्बेज आउट तुम्हें क्लैरिटी नहीं है तो टूल को कहां से ठीक है तो सी में लिखा चलता है पाइथन में लिखा चलता है हार्डवेयर में ना हार्डवेयर में सोचना पड़ेगा ही ठीक है तो हाफ एडर से काम चल रहा है तो फुल एडर क्यों चाहिए राइट अननेसेसरीली you are increasing the delay and area every half adder there will be two more three gates rather additional one half adder plus OR gate right and critical path has also one right okay so how the architecture should look like right inverted the input plus one now how are we going to get that inverted out OD is another option right we do have different ways to invert the output. One is simply using other is using NOR gate. Okay. Let us look at these options. The other is okay. This is A. I want this to be A bar. If it is A, I want this to be A bar. Under what circumstances they will work like this? What should be the other input?
It is also a
I want to connect this pull up or pull down. So tell me in pull up and pull down terms. I want one to be connected to VCC, other to ground. So if here it is one, what will happen? Output will always be 0, right? So there is no inversion, right? But output will be always 0. And if I connect this to ground, then it will be a complement, right? Got it? Why I change my letters later on? Okay. This is active low inversion here you want to do. If your interest is to invert the design output with active low enable, so you can say that enable with active low enable, inverter with active low enable signal. How about this? Inverter with active high enable signal. Right? Agreed? So now you have added programmability. Okay, either you want inverted output or not. Under one circumstances, one will give always output is equal to 0, other will give output always equal to 1. Okay, and you can create a flip flop here to tell you what is the correct methodology to use this one. And how about this? If it is when it is 1, A bar. When it is 0, I can capture my data in true or inverted format. Okay, which was not possible there. It was either emitting 0 or 1 or inverted values. Right. So inversion is also under our control. How we want true signal or all values to be 0 or all values to be 1 or inverted signal or true signal or inverted signal. Depending on that, नहीं तो मैं नहीं दिखा सकता था इन्वर्टर लगा के. Right? Agreed? Now it is under your control, and now that is what typically you are seeing in the books. Okay. I'll okay. Right. Now it is controlled action. If you are doing this is equal to 0, you know you are getting true numbers here. Okay. Otherwise, it is complemented. So now I'll remove this. Okay. Now what will happen? When I connect it here, this becomes control signal, right? And when it is equal to 1, output is 2's complement. Otherwise, हाँ? Otherwise क्या होगा? D in plus, if it is 0, here the number is same, right? D in plus 0, right? So same number, either same number or 2's complemented number. Okay, choice is yours. Now I will add complication. I want either 1's complemented number or 2's complemented number. Okay. Okay, तो क्या करना पड़ेगा? हाँ बैटर डेटा आएंगे तो क्या होगा? कॉम्प्लीमेंटेड आउटपुट 2's कॉम्प्लीमेंटेड नहीं मिलेगा। 2's कॉम्प्लीमेंट में तो चाहिए ना हमें। ओके, तो अब 1's कॉम्प्लीमेंट करने के लिए अब क्या हो सकता है? What may be, now there may be two different control signals, right? And you can include a mux here, right? And which will govern this, either this or this. It is your design, no? You are the architect of the chip. You decide what you want. Right, and then this will be the final output. You discard the previous output. This. Okay.
कैरी को अलग और शोर को अलग करके
तो ऑप्शन देखने पड़ेंगे हमें, ठीक है? So you make this common and make this as another select signal. Okay. Depending on that, you can decide what is the output expected. ठीक है? ये सारी कहानी होगी एक एल्गोरिथम के साथ। तो मुझे ये सारा करना ही नहीं, मुझे दूसरे एल्गोरिथम पे खेलना है। दूसरा एल्गोरिथम क्या बोलता है? टूज कॉम्प्लीमेंट, दूसरा एल्गोरिथम। Start from LSB, find out first non-zero bit. Okay, so that is this. Okay, so up to that, write the number as it is, and rest of the bits should be complemented. Right? That is the second algorithm. I am interested in implementing this. I don't want that rot solution. तब तुम्हें वही सॉल्यूशन देंगे जो घिसा पिटा है। अब उसमें भी वो फुल एडर है, हाफ एडर में नहीं पता है। अब ये कैसे करें? जोर से बोलो, इन दिस नंबर इट इज दिस, देन हाँ तो पता है ऐसे बताओ क्या हो रहा है, राइट? ओके, दूसरा Okay. Control is equal to 0. What is the output here? Is D. Okay, we are least worried about it. Okay, right now. Okay. So first of all, let us take control is equal to 1. That is pretty easy to understand. Okay. Control is equal to 1. What will happen? All the XOR gates will be, all the OR gates will be sending output is equal to 1 because this line is 1. If this is 1, it is 1. Then this input 1, so this is 1. This one is 1. Right? So by default, this chain will become all ones. Correct? And one inverted, one XOR D. So here you will get complement of D. So one's complement, right? So when 1, it is one's complement. When 0, what will happen? There will be no more progression on this line. It will copy what this line is. Okay, so let us look at the number. Okay, maybe two numbers we can say. Okay, what will happen? 0 and control signal is 0. Okay. So this is 0. And this being was also 0, right? So 0, 0, this will be 0. Right? 0, one input, other input 0. How about this? 0. How about this? 0, 0. What is output here? 0. What is output of this? 0. And this is 1. So output here is 1. How about this now? 1 is captured. How about this? Okay, this will propagate. Could I find the first non-zero bit? First non-zero bit is here, and now henceforth it will propagate, and the rest of the bit pattern will get complemented. Hence, if you look at the bit pattern, it is to complement output. Is it? Okay. So we will take another example. Okay. And highlight with other number values. Maybe let us take another number. Whatever number you are suggest, you suggest. Is it okay? Or anything else? Okay, you may be interested in some other bit pattern. चलो इन्वर्ट करना है ना हमें. तो ये बिट 1 करते हैं, ये बिट 0 करते हैं. अब क्या होगा? With reference to this will be. Now I am looking at this bit pattern, right? And controlling 0, 0, 1, 1, right? What will be the case here? Control signal is R1 now. So this is obvious to complement. So what will be the complement of this? Is it 2's complement of the given number? This is the circuit which is available in the ODE book. Okay. I have given this design in this. Why you want to implement the algorithms as they are. Okay. So some points I have tried to include, but not all I could succeed because of page limits or percentage of material which I was supposed to change. But in the coming revisions, I'll be updating all. Majority of the places you will find. Timing delay concept, number of logic levels, how many gate delays will have propagation delay. Because if you don't introduce that in the elementary level, again you need to restart. Okay, starting from basic. So, okay. Now next. Okay. Suppose we want to do some function. Okay. Maybe we could change this. Okay. A B bar C plus A B C bar plus A bar B C. Maybe this is the function given to me. Okay. And now this function is, if you look at this function, there are two different polarities for each literal. A is available in true and complemented format. Same is the case with B and C. Right? So both polarities are available. So sometimes this is called as a bipolar function or binet if you are in the neural networks. Binet or bipolar. If a particular literal is used in our entire function as in single polarity, let it be all positive or all negative, then it is called as a particular literal is unipolar. Okay. And if all terms are in single polarity, then it is called as a unipolar with whatever is the polarity. If all zeros, all are in true format, then positive polarity function. If all terms are negative, then it is negative polarity function. Okay. Now my task is to convert it into unipolarity. Okay, my chip is having unipolar implementation. आपने देखा होगा पास्ट ट्रांजिस्टर्स वगैरह वगैरह में ये सारा चीज आता है, राइट? तो अब यूनिपोलर में कन्वर्ट करना है, and it should be logically equivalent. I should not change my function output. ओके, ये टास्क और इसके लिए जो प्रिलिमिनरी रिक्वायरमेंट है वो सारी हो चुकी है. There's nothing. ठीक है, तो अब कुछ कुछ चीजें हैं जो अंडरलाइन आपको समझनी पड़ेगी. Is it SOP? Sum of product? Okay, maybe 8 possible combinations, and you have got 0 1 0 1 somewhere. ठीक है, क्या हमें राइट दिया है किसी ने कि I can apply this input as well as this input at a time to that SOP, to the combination circuit? Can you do that? No. We apply one set of input at a time. Agreed? अब देखो मैथमेटिशियंस इस पे खेलते हैं, उनका स्टाइल अलग रहता है. ओके, से फॉर टू एग्जाम्पल, ओके, 0 0 0 1 1 0 1 1 and truth table y is equal to, let's say, 1 0 1 1. ओके, अब मैथमेटिक्स वाला क्या करेगा? हाँ, this is a 1D array, right? You want to create it. I'll go with another method. Okay, what is that? The first is 1, others are 0. Okay, is one vector. The other vector with this is equal to 0, this is 0, 0, 0. Okay. The third combination is 0, 0, 1, 0. And fourth combination is what is the resultant of matrix? The one which is output vector. Alright. So now I am decomposing the output vector into 2 to the power n possible combinations. Correct? Mathematically, I am not doing wrong. Because I also know that I can either apply this stimuli or this stimuli. I cannot apply both at a time. Agreed? So as long as you are following this, what does that mean? The canonical form of this expression is nothing but this is A bar B bar. This is A bar B. This is A B bar. And this is A B, which is nothing but function A B is equal to this. And is nothing but summation of this plus this plus this, which is nothing but y. Agreed? Too simple. So now I'll try to change. Number one, all
This matrix, column matrix, are actually presented as Y.
yes, y is represented in different way. One location from here, other 0. Okay. So here it is 1, so it is 1. This is 0, so this is 0. This is 1, so this is 1. This is 1, this is 1. Other places it is 0. Okay, that is what is the input combination. When A bar B bar, output is 1. When A bar B, output is 0. Other places, obviously, this will produce output is equal to 0. Agreed? So, now, what does this imply? All the terms are mutually exclusive. Agreed? Because no terms, two terms are coming at a time, one at a time. So mutual agreement exclusive हो गया. Now you go back to your PLA, PLD, and you will find that there is a XOR sometimes. Why? Because it permits output and or SOPs and or implementation. That OR gate can be replaced with XOR gate. Under this consideration, if I use this as a programmable inverter, SOP can be turned into POS. Isn't it? SOP का कॉम्प्लीमेंट क्या है? POS है. तो XOR का मैं अगर कंट्रोल कर दिया तो क्या हो जाएगा? कंट्रोल इन्वर्टर है, तो SOP को मैंने POS में कन्वर्ट कर दिया पहली बार. और अगर POS मैप किया है तो SOP में ट्रांसलेट होगा. समझे? PLD में XOR क्यों आया? ओके, वो ऐसे ही नहीं पागल कुछ भी इसमें लगा के देने के, उसका इंटरप्रिटेशन कुछ अलग है. ठीक है. तो अब यहाँ पे कितने टर्म्स है? 3 टर्म्स है. POS में जाऊंगा तो कितने टर्म मिलेंगे? 5 टर्म लेफ्ट ओवर. ठीक है ना? SOP कब होता है? When all mean terms are 1. What does it mean? Other terms are 0. Other term 0 मतलब कितने टर्म 0 हो गए? 5. ठीक है. तो आपको किसी ने अगर POS बोला है इंप्लीमेंट करो, तो आप क्या कर सकते हैं, 5 टर्म इंप्लीमेंट करने की जगह 3 टर्म इंप्लीमेंट कर सकते हैं और इन्वर्ट कर सकते हैं। तो आप ओके, तो कॉम्प्लीमेंट्री फंक्शंस, ओके, तो पहला ऑप्टिमाइजेशन वहां पे आता है, डिपेंडिंग ऑन नंबर ऑफ एक्सप्रेशंस। ओके, नंबर ऑफ, अगर इसमें अगर मेरे पास 5 टर्म होते या 6 टर्म होते तो मैं कभी नहीं रियलाइज करूँ, मैं पीओएस रियलाइज करूंगा क्योंकि 2 टर्म इंप्लीमेंट करूंगा और पीओएस का कॉम्प्लीमेंट करूंगा, एसओपी में आ जाऊंगा आसान। ठीक है, एरिया और क्रिटिकल पाथ। ठीक है सर, ये सोचने की बात है, इंटरेस्टिंग बात है, अगर इंटरेस्ट लेंगे तो। ठीक है, अब यहाँ पे एक थंब रूल लगाऊंगा। ओके, अगर ऐसे है तो is it possible to do, पहली बात, ठीक है, मैं तो ये चेक करूंगा अगर होता है क्या, क्योंकि म्यूचुअल एक्सक्लूसिव है। ठीक है, फिर मैं चाहता हूँ दूसरे आइडेंटिटी पे। ओके, तो दूसरी आइडेंटिटी क्या बोलते हैं, ठीक है, इवन नंबर ऑफ टाइम्स इफ टर्म इज देयर देन इट विल कैंसल, लेकिन अगर 1 के साथ है तो कॉम्प्लीमेंट होगा। ओके, चलो क्या होगा, कोडिंग के लिए तो मुझे आपको